In this video, we are going to present our advanced machine learning's first assignment. The topic of this assignment is comparison between ensemble and single model. We are presenting this assignment to Mrs. Akshata AMS, Assistant Professor, AML Department. My name is Jaydev Amar and I am joined by my team members Ashish Raut, Nitin S and Rahul Arji. In the field of machine learning, we have face often a choice. Should we use a single powerful model, or we can achieve better results by combining a wisdom of several models? This is the core question we will be exploring today. The next slide is introduction. Our analysis aims to directly evaluate and compare the performance of single machine learning model against what is known as ensemble model. For this comparison, our single learner is a decision tree classifier. You can think of a decision tree like a flowchart. If you ask a series of if-else loop, it is powerful, easy to interrupt, but can sometimes be proven to errors if it is become too specific to the data was trained on. Our ensemble model is a random forest classifier. As the name suggests, a random forest isn't just one tree, it's a collection of ensemble, or multiple decision trees. It combines their individual predictions, typically by taking a majority vote to make a final, more dramatic decisions. The idea is the term of model can correct each other's mistake. This leads us to our central hypothesis. We predict that the ensemble model, the random forest, will demonstrate superior performance and better generalization on unseen data when compared to the single decision tree. We believe the wisdom of crowd will prevail. The next slide is data set and preparation. For our experiment, we select the breast cancer dataset, which is available in scikit-learn library. The dataset is ideal for our purpose because it presents a clean binary classification problem, classifying a tumor as either malignant or benign. The dataset is well structured, containing 569 instincts or patient records and 30 numeric features derived from the digitalized images of a cell nuclei. Before we could train our models, we performed some essential pre-processing. First, we loaded the dataset and checked for its completeness to ensure there were no missing values and no other disrupt could happen to our model training. Most importantly, we split the dataset into training and testing dataset in the ratio of 80-20. The next slide is model training. First, we have two models here. The first one is decision tree classifier and the second one is random forest classifier. First, we trained the decision tree classifier where we fed 80% training data into the single decision tree classifier. The model learned the pattern from the data to build its flowchart for rules. The model serves as our baseline, representing the performance of a single learner. Next, we trained our second model, the random forest classifier. We used a random forest classifier and trained it on the exact same training data to ensure a fair comparison. A crucial parameter was set here was n estimator is equals to 100. The parameter tells that the model to build an ensemble of 100 individual decision trees, which means 100 trees were trained on a slightly different random samples of training data, which encourages diversity within the forest. By training both a single tree and a forest of 100 trees on the same data, we have perfectly set the stage to compare their performance and determine if the ensemble approach truly provides an advantage. The further part will be continued by my teammate Ashish.
Thank you, Jaidev. Now let's come to the evaluation metrics. Here, basically, we are considering the four performance measures, namely precision, recall, F1 score, ROC score, and the AUC score. Here, the precision means it measures how many of the predicted positives were actually correct. and its formula is true positive divided by the sum of true positive and false positive. Next, let's come to recall. Recall is also known as sensitivity. Basically, it measures how many actual positives were correctly identified, and its formula is true positive divided by the sum of true positive and false negatives. Next, let's come to the F1 score. The F1 score is the harmonic mean of precision and recall. Lastly, we come to the ROC AUC score. It tells how well the model distinguishes between different classes. For example, the positive and negative. A value of 1 is a perfect model and zero point 0.5 is random guessing. Next, let's come to the methodology. Here, the below table compares both models based on the metrics above. As you can see that the random forest has overtook the decision tree in all the criterion. So we can conclude that the random forest classifier clearly overperformed the single decision tree model in every matrix. This means it was more accurate, caught more true positives, and distinguishes classes better. And the further topic will be explained by my teammate Nitin.
Thank you, Ashish. Next, let's look at the ROC curve, which helps us understand the model ability to classify correctly. The ROC, or Receiving Operating Characteristic Curve, plots the true positive rate against the fake positive rate. A model performs best when its curve is closer to the top left corner, meaning it has a high true positive rate and a low false positive rate. In our comparison, the random forest curve has an AOC value of 0.995, while the decision tree AOC is 0.932. A higher AOC means better classification performance. As we see, the random forest line is much closer to the top left corner, indicating that it's almost perfect at distinguish between the malignant and beginning cases. So usually the ROC curve confirms that the enable model performance far better than the single model. Next is like analysis, reducing variance and improving generalization. Now let's discuss why random forest performed better. First, like single decision tree often suffers from the high variance. They can fit the training data very accurately but fail to generalize an unseen data. In simple terms, they may learn the noisy instead of the pattern. The random forest reduces his problem using two main techniques like bagging and feature randomness. First, bagging or bootstrap aggregating means each tree is trained on a different random subset of the data. This creates many diverse models. Second, feature randomness ensures that at every split in a tree, only a random subset of feature is considered. So no single feature dominates across all the tree. When we combine these diverse tree, their individual errors cancel each other out, resulting in a model that is stable, accurate, and better at generalization. This is why enables like random forest performs more uh, cons- uh, consistently and avoid overfitting. Next slide will be explained by my friend Rahul. Thank you.
Thank you, Nitin. Now let's come to analysis. How ensemble control overfitting. Overfitting occurs when a model memorizes and trains data instead of learning underlyingly patterns. Ensemble solutions. Ensemble controls overfitting by combining the output of multiple models. As my friend Jaida said that we use decision tree and random forest two ML models to combine as an ensemble solution. The strength of an ensemble comes from diversity of its learners. While one tree might overfit to a specific part of an data's noise, may other tree in the forest will not. By averaging these predictions and collective decisions is much less sensitive to the noise and outliers in the training data. These led to smoother decision boundary and more robust model. Finding the random forest classifier and an ensemble model demonstrated significantly better performance than single decision tree across all key metrics. Reason: an ensemble method effectively reduces model variance and control overfitting by combining multiple diverse learners. Impact for many real-world classification tasks, using an ensemble model like random forest is highly effective strategies to achieve higher accuracy and create more robust generalization model. Here, the conclusion says that the random forest is highly effective. Thank you, everyone.
Yeah, now we'll go on to the code part. As you can see, we have imported all the necessary libraries here. We have imported all the necessary libraries, and we have split like for the y-axis and x-axis for the accuracy curve. We have split the data where data is in the x-axis and target is in the y-axis. And here the splitting of data into training and testing sets, like as we said, 80% for training and 20 for the test. We have split here. Now we have initialized the models. You can see here we have initialized decision tree classifier model and the random forest classifier model. Here we are evaluating the models. You can see here we are evaluating the models as requested. We have done precision, recall, F1 score, and ROC, AUC curve. Then to plot the curves, we have given the requirements here, and we have set them to plot the curve as the true false rate, false positive rate, and true positive rate. For the plotting, we have given the title as ROC curve comparison. Now let's run this. Now let's run this and start. We'll see the ROC curve now. Yeah, now you can see that we have got the output in the form of a pictorial output, where you can see that blue lines, the inner line, which is the blue line, is represented by decision tree, and the outer line is represented by random forest. This is the ROC curve comparison. And here you can see that the matrix analysis of the models. Model decision tree random forest precision is 0.95, whereas random forest precision is 0.958. The recall of decision tree is 0.95, whereas random forest recall is 0.98. F1 score is 95, 0.95, whereas random forest F1 score is 0.97. The ROC AUC curve of decision tree is 0.94, whereas random forest is 99.52. You can also observe the ROC curve for both decision tree and random forest here. So this is the end of our assignment. You can see the results on the screen. So thank you everyone.